In a previous video we wrestled with the concept of rate of reaction and introduced the concept of the rate equation. In this video we're going to look at order of reaction, which you might have heard me talk about in the previous video, and a new concept, rate determining temperature. Order of reaction doesn't necessarily have a definition per se, however it is a concept you need to be aware of and you need to know how to apply. I'm going to recap where order of reaction comes into the rate equation. Order of reaction is the number to which the concentrations of the reactants, we'll take it as A and B, are raised, i.e. M and N. And I'm just going to recap again that M plus N is the total order of the entire reaction. The order of reaction can be inferred from a graph. This is a graph of a zero order reaction for concentration against time. The way you can infer the order is by drawing half-lives on the graph. So if the starting concentration is 1, the half-life will occur when the concentration is 0.5. So we draw a line along there till it meets the curve and goes down. This is a half-life. Then we take the next half-life, which will be 0.25. From the graph we can see that the half-life has halved. So if we take this as this length as x, this length will be a half x, or x over 2. And that's typical of a zero order reaction. It's also worth noting that the graph is concentration against time, so the gradient of this curve would be concentration over time. And we already know this from a previous video that concentration over time equals rate. So the rate can be gathered from a concentration time graph by taking the gradient. This is a rate concentration graph for a zero order reaction. We can see that as concentration increases, rate does not, rate stays constant. So we can say that concentration has no effect on the rate. This is a concentration time graph for a first order reaction. If we take the half-life from 0.5, the half-life from 0.25 again, we can see that the half-lives are the same, x and x. So we can say that there is a constant half-life on this graph, as opposed to the halving every time on a zero-order reaction graph. To plot a rate concentration graph for this, you need to take the gradient at multiple points on the curve. So you need to take tangents from the curve. So if you take one there from the initial one, oops, sorry. Take one here from the middle. And if you can plot these gradients onto a rate concentration graph. This is a rate concentration graph for a first order reaction. I'll just draw lines to show the value of rate against concentration per arbitrary unit. You can see that if concentration doubles, draw a line up here, so does rate. This is a concentration time graph for a second order reaction. If we take the half-life from 0.5 and the half-life from 0.25, we can see that the half-life has doubled. So this would be x and this would be 2x. Again, we can take the gradient from the curve by taking tangents, by doing concentration over time, and we can plot a rate concentration graph from. Here is a graph of rate against concentration for a second order reaction. We can see that if the concentration is 2 arbitrary units, rate is 4 arbitrary units. If the concentration increases by 2, by a factor of 2 rather, the rate increases by a factor of 4, or 2 squared. And similarly for 5 arbitrary units, the value of rate is 25, which is 5 squared. So we can say that rate, which I'll do as r for the time being, is proportional to concentration squared. So if we put our constant in, we get r equals k concentration squared, which is our rate equation for this second order reaction. Because we can do that, we can say that because it's proportional to concentration squared, we can plot a graph of rate against concentration squared to form a straight line graph. Rate determining step. Reactions have mechanisms, and mechanisms have stages. The stages of mechanisms go at different rates. And similar to how a horse and carriage limits the rate of the cars behind it, the slowest step in a mechanism limits the rate of reaction. This is the rate determining step. This is the rate equation for a reaction. The rate equation is closely linked to the rate determining step. Is the rate determining step for the same reaction. Now there is a link between the orders with respect to H2 and ICL and the stoichiometric numbers of the rate determining step. Whereas both reactants are order 1, and they both have one molecule in terms of stoichiometry in the rate determining step. You can work out the rate determining step from the rate equation using that same logic. Because they're both order 1 with respect to themselves, there must be one molecule of each reacting to produce the products, stoichiometrically speaking, of course. This is the second stage of the mechanism. You can see that HI is an intermediate, so this gets cancelled out in the overall equation. This is a basic skill for writing out mechanisms. And here is the overall equation. You can see that the HI is cancelled out, and the HI's cancel out, and you can collect up the products from this side. HCl, HCl, and I2. Here is a table showing the units of K and the rate equations for the different orders of reaction. These are m plus n values. This is the total equation, total rate equation. So you can see for 0 order, this is the rate equation, and the units of K are moles, dm minus 3 at seconds to the minus 1. First order is, this is the equation, and its units are seconds to the minus 1. Second order, R equals Ka to the 2, moles to the minus 1, dm3, s to the minus 1. Third order, R equals Ka to the 3, moles minus 2, dm6, seconds to the minus 1. Some people would have you write the more positive values, such as, like, for this one it'd be dm cubed first. However, I think it's more logical to write as moles first, then dm, then seconds. Purely because that's how we write concentration, it's easier to remember it that way.
Got this riddle figure, do you? Someone must have sent you to orchestrate a shell game against the calluses of our hearts. I hate your subtle beauty, do you? The way you do, I slow dance me and beat like a million hummingbirds when I draw closer. And the slope of your nose I detest. It's the kind that drove pharaohs crazy. Touch me, I'm a hornet's nest, sinking in Egyptian levees. Most of all, I hate the way that I miss your sight.